Hello, Assalamu alaikum warahmatullahi wabarakatuh. This is Hassan Abdulrazak Ahmed with matric number BE21009. I'm here with my group number 7, for section 5 and 6 in a signal and system course. So this is introduction for our report, for our project. In the dynamic domain of electronics, the imperative to manipulate circuit is non-negotiable. This project takes a sophisticated approach leveraging Fourier and Laplace analysis to dissect the basic of electronic circuits, aligned with the outcome domain LOD2, program learning outcome PLO2, and competence C4. Our goal is to decode the nonsense interplay between input signals and circuit responses. Basic electronic circuits and diverse applications demand a profound analytical arms. Fourier analysis to construct integrate signals into elemental sinusoidal components, unveiling the essence of frequency domain characteristics. Meanwhile, Laplace analysis integrates in a complex algebra, unveiling circuit dynamics and transit responses, offering insights into temporal behavior. Our journey aligns seamlessly with the LOD2 applications of theory to practice. PLO2 emphasizes on advanced mathematical tools, and C4 focuses on employing specialized techniques for circuit analysis. The subsequent sections will unfold the methodology from circuit curation to Fourier and Laplace applications, illuminating the input-output nonsense of basic electronics. This exploration is not just about circuit understanding but also about arming ourselves with the analytical acumen essential for tackling real-world challenges in electronic design and signal processing. We navigate the profound themes of Fourier and Laplace analysis, advancing our comprehension and capabilities in the realms of basic electronic circuit. So that's our introduction. Thank you so much.
Wabarakatuh. My name is Muhammad Ashia Bimanasi. So today I want to present my part, which is a methodology. This study describes the Fourier and Laplace analysis methodology used to analyze simple electronic circuit. The main goal is to illustrate how important these mathematical tools are for comprehending and creating electronic circuit, with a particular emphasis on filter and amplifier. The introduction offers a synopsis highlighting and the applicability for Fourier and Laplace analysis in fundamental electronic circuit and delineating the particular goal of the investigation. In the background portion, fundamental knowledge of simple electronic circuit is established, and important theoretical ideas that are necessary for the analysis are introduced. Using previous research and literature on the topic, a true literary study condenses important theories and concepts associated with Fourier and Laplace analysis in electronics. The pace of circuit selection in particular. And then Methodology is coding. This is our coding. First, second, third, fourth, five, six, seven. And then the second part is result and analysis. So this is a manual question for question 2. Question 2, time domain signal. This is the output of the signal ST45 harmonic. And then is this output for the signal ST410 harmonic, and then this is output of signal ST420 harmonic, and then for the frequency domain signal, figure 4 signal is for the 5 harmonic, frequency domain signal for 5 harmonic, and this is a frequency domain signal for 10 harmonic, and then the is frequency domain signal for 20 harmonic. And this is question 2. The function can be represented mathematically as a sum of sinusoidal function or harmonic using the 4 series. Complex exponentials are used in the exponential synthesis equation to express this series. More harmonic improve conjugation and the accuracy which since the original function is represented, but they also add to the computation complex. Waveform complexity is influenced by the harmonic selection, which made it approved for creating complicated signal synthesis. The amplitude in this result is 1, and the more harmonic they are, the more the signal will be reasonably deep. And for the question 3 is lower pass filter. And it is a frequency response for lower pass filter. Question 4, time domain signal after low pass filter. So this is a filter signal for 5 harmonic, and then this is a filter n equal for 10, literally signal 10 harmonic, and this output for the 20 filter signal 20 harmonic. Frequency domain signal after low pass filter. This is a frequency domain signal for 5 harmonic, and then frequency domain signal for 10 harmonic, and then frequency domain signal for 20 harmonic. Result analysis 3 and 4 in this magnetic based project, an RC low pass filter was implemented with a cut-off frequency determined by the formula FC equal to 1 per 2 by RC. The filter design using MATLAB is signal processing tool, filter resistor and capacitor component. MATLAB scripts were implemented for Fourier confusion calculation and signal synthesis through the exponent synthesis equation. The MATLAB driving analysis involved comparing the visual reconstruct signal with the original filter signal. Incorporating the specific of frequency formula in MATLAB provide a computation exploration of the filter frequency attention property. This MATLAB result contribute to a comprehensive understanding of the filter behavior, shedding light on an impact of on the spectral content of filter signal. A frequency response plot show how the low pass filter change the signal in terms of frequency. It is a graph that help us with part of the signal is like through which part it reduces. For a low pass filter, it allows the lower sound to pass but tone down the higher one. In our case, we set the filter to let through below 600 kHz. Question 5, standard domain circuit. This is a Simulink low pass filter circuit for time domain, and it is a subsystem. Time domain waveform. Verify Simulink waveform before low pass filter. Figurating waveform after low pass filter 5 harmonic. And then figure 70 waveform after low pass filter 10 harmonic. And then waveform after low pass filter 20 harmonic. Frequency domain circuit. Simulink low. This is a picture of Simulink low pass filter circuit for frequency domain. And then is a subsystem. Frequency domain waveform. Waveform before low after filter. This is the picture for the waveform before low pass filter and waveform after low pass filter. Analysis question 5. The performance of the construct RC low pass filter circuit. The frequency response of the filter was internally examined using MATLAB. Confirm that cut of frequency align with the design specification derived from the formula FC equal to 1 per 2 PyRC, the time domain analysis show the impact on the waveform with the filter effectively attuning higher frequency while presenting lower one. For a series analysis provide the inside the frequency content from the filter ability to select the allow pass below the cutoff frequency. Visual comparison between the original and filtered signal using the filter performance. Demonstration is proficiency in shaping the output. The experiment successful showcase the construct RC low pass filter combined to alter the frequency characteristic of the input signal. That's all for me. Thank you.
Hello and good evening. My name is Sailesh Analaki Gopalakrishnan, metric number CE210068. Today, I would like to explain our project for question number 2. So based on question number 2, we have to do a further series analysis of the given signal using for time domain 5, 10 and 20 harmonics using the tau value which is zero point 0.5. So for our section, the given value is 100 kilohertz and 600. So based on that, we have come out with this coding as you can see. So the FO value is equals to 100 kilohertz, TO is equals to 1 over FO value, tau equals to 2.5, and these are the values of T, X, T, X, N. For N equals to negative 2020 if, else if, and these are the codings we use. So when we run the coding, so these are the signals value before low pass filter. This was our outcome, and for the next coding, this is for so this is for our frequency domain. So same goes for the value of FO, which is 100 kilohertz, and the value of TO is 1 over FO. Tau equals to 0.5 times TO. And our if else statement. So after running this code, this was our rough value before low pass filter. So that is all from me. Thank you.
DE210008. Now I'm going to explain about question number 3. Question number 3 is construct a low pass filter using MATLAB with frequency response characteristic as that given in figure 1a, where FC equal to cutoff frequency and gain of 20 log. Now we see the coding for low pass filter in MATLAB. This is the coding. FC is equal to 600 kilohertz. This is our cutoff frequency in hertz. Our frequency range is f log space 07300. The transfer function is h equal to 1 divided by 1 plus 1 if times with f over fc. Transfer function of the system is this. Then we calculate the gain in decibels. Gain is equal to 20 log 10 f. Then we plot the frequency response. This is our frequency response for 600 kilohertz fc. Now I'm going to explain about question number 4. Question number 4 is about analyze the output of the filter both in time domain and frequency domain. For the first one, time domain, here is the coding of the first time domain. For the frequency, we have used 100 kilohertz. This is for TO 1 over our 100 kilohertz. The tau will be 0.5 times TO. Then there are other equations. The low pass filter parameters are FC 600 kilohertz. Then there are other equations. We did for three harmonics which are 5th, 10th and 20th. This is for 5th harmonic. We use this equation. For 10th harmonic, we use this equation. For 20th harmonic, we use this equation. Then we plot all the graphs. Then for xn, we use this equation. For xt, we use this equation. Now we simulate the coding. So here we can see the difference between the before low pass filter and this one is after low pass filter. This is for 5th harmonic. We can see the noise reductions. So for the 10th harmonic, we can see the noise reduction. And for 20th harmonic, there is no noise. We can see how the low pass filter transform these signals for following harmonics. Now let's see for frequency domain. For frequency domain, same we use F4 100 kHz, TO equal to 1 over F4, tau equal to 0.5 times TO. Then we perform FFT for 5, 10 and 20 harmonics. We use this equation. For filter the frequency domain with the cutoff frequency FC. Our FC is 600 kHz. Cutoff index is equal to round off FC times n divided by Fs. We did for 5th, 10th and also 20th harmonic FFT. Then we plot the graph. This is the xn equation and xt equation. For frequency domain, we can see the difference between this one is before low pass filter, this one is after low pass filter.
So the value xt filter 20 harmonic based on this value 20. For the time domain, this is the xt. Just highlight and paste it for 5, 10, 20. We just use it from there. And if we run, so we will get this type of graph. Just have to wait for it to completely form. So this is after the low pass filter circuit. And for the frequency domain, this is the frequency domain circuit. This is also same. the XT is from a workspace. Just copy, highlight, and paste it here. So this is the subsystem for the low pass filter circuit. And if we run this, we should be able to get this type of circuit. So that is all from me. Thank you.
So hello, my name is Valerie Melanie. My matrix number is AE220120. So for this assignment, I'll be presenting question 7's manual calculation as well as the simulation. So from here, it is given that FO is equals to 100 kilohertz, FC is 600 kilohertz, and we assume the capacitor is 47 nanofarad. And using the formula, which is FC equals to 1 over 2 pi RC, we get the value for the R, which is 5.64 ohm. Therefore, our value for capacitor is 47 nanofarad and the resistor is 5.64 ohm. So when we go to Proteus, this is the first circuit that I have simulated, and as you can see here, the value for the R is 5.64, the capacitor value is 47 nanofarad, and then I drag the probe for the voltage of the capacitor to get the frequency response, and this is our graph. So it is going downwards. For the next simulation, I've used this signal generator as well as the oscilloscope, and then when we run the system, we get this. Hold on. Alright, so for the VSM signal generator, this is the input value that I've put, 50K for the frequency and 1.0 for the amplitude. And then for the channel, this is the value, and then we'll get 2 of this graph. So that is all for my part. Thank you. So hello, my name is...
In a conclusion, the Fourier series analysis, signal analysis in the time and frequency domains, constructions of low-pass filter, and simulations provide valuable insights and practical tools for understanding and processing signals. By decomposing signals into their harmonic components, we can analyze their frequency contents and characteristics. The low-pass filter allows us to selective high-frequency components, while simulations validates the analysis. Overall, the combination of Fourier series analysis, signal analysis in a time and frequency domain, low-pass filter constructions, and a simulation provides a comprehensive understanding of the given signals and their processing. These techniques are valuable tools in signal processing and circuit design, allowing us to analyze and manipulate signals effectively for various applications. So that's our conclusions for our report.